1.2, properties of limits, properties of limits. This section is going to be pretty darn easy, pretty darn fast. In fact, I think we'll finish it today. How's that sound? Yeah. It's going to have a very similar feel to evaluating functions, except keep in mind that evaluating a function is finding the function value, the location of the bridge, and we're going to be evaluating limits, so the notation is going to be slightly different. Now, I can go through this whole chart here pretty quickly, and you might be like, what? But once we start using it, you're going to be like, oh, that's what, okay? So here's what the first one says. If you have the limit of a sum, it's equal to the sum of the limits, okay? Question? The limit of the sum is the sum of the limits. What that means is, if you're evaluating a limit and you have multiple terms, whether they're added or subtracted, you can evaluate each term separately, independently, and combine the results. That's all it means. If you're taking the limit of a constant times a function, you can pull the constant multiple out front, take the limit of the variable part, and then take the result and multiply it by the constant. Works with a product as well. The limit of a product is the product of the limits. So essentially, evaluate the variable parts first, and then combine your results using whatever math is there implicated, plus, minus, multiplication, and number 4 says it works with division as well. Number 5 says it works with exponentiation. So you can actually bring the limit inside, evaluate the function it sees, and then exponentiate your answer. So you'll see those in action here in just a second. Number 6 is an important one. And I want to kind of look at that a little bit more closely, because this one is composition, where you have one function embedded inside of another. So to kind of set the table for that, let's say I have f of 1 equals 3 and g of 3 equals 17. Okay? And if I ask you to evaluate g of f of 1, how would you do that? You would multiply 3 by 17? Well, careful. This is not g times f of 1. This is g of f of 1. So it's composition. So you would actually have to work from the inside out. You would have to first plug in a 1 for x into your f function. So 1 is the input, but of course, what would the output be? 3. So you would replace f of 1 with 3, and now the output for f of 1, which is 3, becomes the new input for the next layer, which is g, right? What's g of 3 then? 17. Okay? So it's kind of like a sequential process. The input becomes the output. That output becomes the new input for the next layer. It works the same way with limits. We just have to keep our x values as limit values, not plug in function values. So here's what this one says. If we know the limit as x goes to c of g of x is equal to L, then we can find what the limit as x goes to c of f of g of x is. And I'm going to show you the intermediate step. Because the g of x is on the inside, you can actually rewrite it with the limit on the inside. You could say that's f of the limit as x goes to c of g of x, like that. And now we can evaluate that. So notice that c is the input, and what would the output be? What's the limit as x goes to c of g? L. Well, it's given to be L, right? Now here's where you want to be careful. You do not want to then just call that f of L. In other words, don't just replace this with L, because now f of L is no longer the limit, right? This is the function value. So L is now going to be our input, but it's not the x value we're standing at. It's the new x value we're approaching. So it will equal now the limit as x goes to L on the function f of x. So that's what it's equal to. Okay, so it's still the same idea. Input becomes the output. That output becomes the new input. We just keep it in terms of the limit. Sequential process. Okay, now I just made this ugly expression up down here. If you understand this, you'll get the idea of pretty much everything in the table. Basically, if you're trying to evaluate the limit at an x value and you have multiple variables in that expression, in this case you have an x, an f of x, another x, and a g of x quantity squared, that's what this means, you can put the limit directly in front of your functions and evaluate each of those variable pieces independently and then combine the results, like I said, using the indicated operations. All right? Let's see it in action. What types of questions are you going to be responsible for? Well, example 1. Here you're given a very limited amount of information. You know that you have three functions, f, g, and h. And as you approach the same number, 3, on all three of those, you have different limit values, 8, -2, and 0. That's all you know. You don't need the equations of f, g, and h, and you don't have any other information at any other value of x other than 3. But with those three pieces of information, I claim that we can evaluate the following limits. That is, any combination of those three functions as long as we're approaching 3. So I'm going to show you how the properties work. And once you see it, the way it works, you're not going to have to go through this formal step of writing it out after you get the hang of it. But this is property number 1, first and foremost. This says the limit of a difference will become the difference of the limits. In other words, you can essentially give each of those their own limit. So this would be step 1. The limit as x goes to 3 of twice f of x minus the limit as x goes to 3 of 4g of x. And that would be property number 1. Now, property number 2, if you scroll back up, it says that you can pull constant multiples out front. So in each of those two terms now, property number 2 says I could pull the constants out front. So that becomes 2 limit as x goes to 3 of f minus 4 limit as x goes to 3 of g. And with that written like that, I can now focus on these pieces of information, which of course were given up here. And so now I can substitute. So this becomes 2 times, and what is the limit as x goes to 3 of f? It says it's 8, okay? And then the next one would be minus 4 times the limit as x goes to 3 of g is -2. Yeah. So it almost feels like direct substitution, right? If I had said f of 3 is 8, g of 3 is -2, and h of 3 is 0, evaluate 2f of 3 minus 4g of 3. You would just be directly substituting in. And it is. It's just in the context of the limit. Now, of course, on a free response, that last line would be okay to stop, yeah? Yeah. And we'll keep going. We get 16 minus 8 plus 8 plus 8. And I'll stop right there. I'll call it 24. No, I'll go for it. 24. So there's the answer. Got the hang of it? All right, let's look at B. Rewriting it again one more time. You've got the g of x is the only variable part here, and that's what you need to evaluate. So you can put the limit directly in front of there, and everything else would be the same. So you have beefy blue bracket 2, limit as x goes to 3 of g of x, close beefy blue bracket squared. And now it just comes down to evaluating this, which of course is still -2. So we get 2 times -2 squared. Free response, we're done. Multiple choice, we keep going carefully, and we get 16? Yeah, -4 quantity squared is 16. Good. Yes. The limit essentially can reproduce itself and nestle up right up against any variable, whether it's an f of x or an actual x. And then once you evaluate it, everything else can be, put in there according to the operations. All right, with that in mind, go ahead and try C on your own. And if you don't want to go ahead and write the limit each time, because you'd have to write it 1, 2, 3, 4 times, see if you could do this one just by dropping in values. Of course, if you want to go ahead and write the property out, you can, but you're not going to have to. It's a slow start to the year for pooping dogs. I haven't seen any this whole year yet. I don't know if they're going inside or I'm just missing them. It's a totally different ambiance with all the lights off. Feels more studious, doesn't it? Yeah. It's easier to steal someone's calculator when they're not looking because it's dark. Oh, sorry. No, it's not that dark. Yep, that's right. That's right. So you kind of worked in a circle like that. Yeah, it's okay. If you had the room, though, you would work straight down. Yeah, yeah. But you boxed it, and that's good, because that makes it stand out. Remember, ideally, you're working straight down vertically. I understand sometimes you run out of room, at which point maybe you just make another column and you work to the right. Okay, so I did it here without rewriting the limit, but it would be the cube root of the limit as x goes to 3 of f over the limit as x goes to 3 of g plus 4 times the limit as x goes to 3 of h. And then down here, this is interesting, this x plus 7. There's no f, g, or h, so this would just be the limit as x goes to 3 of x plus 7. So when you substitute then, you get the cube root of 8 over negative 2, 4 times 0, and what do you do with x plus 7? You can just plug in your 3, because you can think of it as just being x, which is continuous. So you plug in the 3 and you get 10. So if you simplify that, then you end up with negative 1. So going from here to here is fine. You don't have to write out the properties of the limits, but know that that's kind of why it works. Now, this type of question, you're very limited because I can only approach 3 and I only have 3 functions. Here's kind of another way to ask a very similar question that gives you a little bit more flexibility and makes it slightly more interesting. I only have 2 functions here instead of 3, but I have a lot more x values. And you now are going to be pulling your own values off the graphs to answer these questions. So having said that, the graph of f is on the left, the graph of g is on the right. I drew these myself, so everything that you're expected to pull off there is going to be a nice integer. So go ahead and see if you can figure out A on your own. And don't necessarily rewrite the properties of limits unless you feel just more comfortable doing that. That's fine. And while y'all are doing that, I'll remind you that there's a volleyball game tonight at 7 o'clock against Reagan in our gymnasium. Ooh, that was fast. Let's see. I got to catch up with you. Let's see. F0 would be 2 squared. Yeah. Combinations of these types of questions make really good multiple choice questions on your test, which will be probably late next week. I can give you a graph like this, and then I can string terms along so that you have to evaluate many of these things and then add them up to get a multiple choice answer. I got 8 on that one there. The next one, notice you have an x squared. So you can kind of evaluate the x squared independently of the g and the f, right? How would you evaluate x squared as you go to negative 3? Just plug it in, right? Negative 3 squared is 9. And then g of x, that'd be the one on the right, at negative 3, let's see, negative 1, negative 2, negative 3. I intended it to be 1. It's not the most perfectly straight line, but you can infer that it's going to be positive 1. And then f of x, the other one, at negative 3, 1, 2, 3, is negative 1. So this one does come out to be just plain old negative 9. So nothing really difficult. Just, where? Well, this is x squared, right? And I'm approaching on A. Times 2. Times 2. Yeah, you wrote it down wrong. That happens. Now, there is one time where I would think actually writing the properties of limits down would be helpful. And it's in this type of example where you have what? G of f of x is composition, because this is the sequential thing. So here's what I would recommend. Put the limit on the inside. You got f of x like that. And so now you can just focus on that, which I think we just did, but I already forgot. So the limit as x goes to negative 3 in general of f was negative 1. So again, here you have to be careful. You can't just replace that with negative 1, because this is still has to be a limit, not a function value. Yeah, so negative 1 is now the value of x we are approaching on the graph of g and not jumping at function-wise. And is there a difference in general between g of -1 and the limit as x goes to -1? Yes, there is. So let's go over here to g and see what the limit is. Here's -1. The limit is what?
1.
Positive 1, right? They're approaching the open circle, which is the limit, whereas the function value is 2. So, yeah, very different. This is 1, not 2. But I guarantee 2 would be an answer choice, right? So I better put right here a not equal sign. So if it starts as a limit, it's going to remain a limit all the way through. And if it starts as a one-sided limit, even on the composition, it'll remain a one-sided limit. So if it's from the left to begin with, it'll stay left all the way through. Okay, I think you have it now. Go ahead and round out this example by finishing off D, E, and F on your own. And I will do them as well and see if we get matching answers. And this is the opportunity for you at home, if you're watching the video, to attempt these as well. Bless you. D is probably the trickiest one of the three. You don't have to keep going here. Once you get D and E, it's game over at D and E. Yeah. I was just messing around. Yeah. Yeah, it's over when you get E.
So why is f of x
On F, let's see. Oops. You got the general limit at -1 on F. So here's -1. The general limit from the left is 1, and the limit from the right is 2. So, yeah.
Okay, thank you.
If it had been a one-sided limit, then it would still work. Okay, let's see how you did. D is actually another composition, because it's not just g of x, it's g of blob, which is x squared. So if you want to bring that inside, you're first evaluating x squared at -1, which is a parabola. It's continuous everywhere, so direct substitution. -1 squared is +1. But it's not g of +1. It's the limit as x goes to 1 of g, which then if you go to the graph of g at +1, the limit is -1. So that's the answer. So another composition. And then the next two are not composition. This one's pretty straightforward. You're approaching one from the left. So So it's 2 times 2 over negative 1 quantity squared. So just make sure you have parentheses in place. You don't want to end up with the wrong type of 4. And on this one here, it's the general limit. And because f of x has a jump at negative 1, you hit D and E. And once you hit D and E there, you don't have to keep going doing everything I did. Once you hit D and E, you just go right to D and E for the answer. So anyway, yeah. So not so bad, right? Multiple choice questions, you can handle that. I might do like, give you the graph, and I might be like this plus that, maybe plus this one here. And so you would just find negative 1 and a 4 and a negative 9 and maybe add them together. Just a way to kind of ask different things. Okay, so shifting gears here a little bit, there's a theorem in this section that closes out the section, and it's a very important theorem. We'll have several theorems throughout the year, and the theorems that have names, like this one's called the squeeze theorem, sometimes it's called the sandwich theorem, sometimes it's called the squishy theorem or the smoosh theorem. Not really, just the squeeze theorem, but they all imply the same thing, right? Food. Have a sandwich for lunch, and I guess you can interchange squeeze, right? Anyone have a squeeze for lunch today? What flavor is squeeze? No, sandwich and squeeze imply what? Compression, yeah, pushed together. And that's exactly what the theorem discusses. So when it's a theorem like this, you're responsible for knowing the if part and the then part, and you're also responsible for formulating an argument using the theorem. So let's take a look at what it says. This is kind of a telltale giveaway. This is a compound inequality, and when you have a compound inequality with less thans like this, then you read it in increasing order. So these are y values. You have 3 functions, g, f, and h. G of x is less than or equal to f of x, which is less than or equal to h of x. So just by reading that, what this says then is the function f of x is physically contained between g of x and h of x, okay? So h of x is the upper bound, g of x is the lower bound, and f of x is contained in between them. It could bounce off of these curves because it's equal to, or it can be strictly in between them. But f is contained by g on the bottom and h on the top. If that's true everywhere except possibly at a single x value, then if we know this, if the lower slice of bread, g of x, and the upper slice of bread, h of x, both have limits of L at x equals c, what does that mean? This bread slice goes to the point CL, this bread slice goes to the point CL. What then can be said about the limit as x goes to c of the function that is sandwiched in between them? It also has to go through L. Yeah, the limit has to equal L. And that's all it says. So to get kind of a real easy visual here, let's let this be g of x right here, just a generic function. And then let h of x be this one right here, maybe like that. Bless you. And let's let h of x have an open circle there and a function value right there. We can let g of x actually exist there if you want. And then we have this other function, f of x, that's contained in between them. So it could be strictly in between them like that, or it could bounce off the curves, you know, it could be equal and look something like that, and then bounce, 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 whatever. And let's say it has a function value right there and an open circle. So this would be x equals c. The red graph, f of x, is going to be contained between g and h everywhere except possibly at c. Well, because h and g pass through the point, or have a limit, I should say, of c comma L, then the red function also has a limit. It's sandwiched in between there. It's kind of a no-duh kind of idea, right? The meat is between the 2 slices of bread. Now, how are we going to use that? Well, I'm going to skip example 3, because I think it's kind of a silly example with the calculator, and we'll just jump to example 4, because this is a very typical type of question. The theorem itself is pretty easy to understand, but how are we going to use it? Well, I'll show you. The first step is in realizing that you're going to have to use the squeeze theorem. So, reading example 4, if negative 3x is less than or equal to g of x is less than or equal to x squared plus x plus 3, find the limit as x goes to negative 1 of g of x. How many of y'all read that right away and you go like, squeeze theorem? You do? What's the giveaway? You have a compound inequality, and you have an unknown function g of x that is between two known functions, and you're trying to find the limit as x goes to -1 of the unknown function. We know nothing about g of x other than it's contained between these two functions there. Now, here's what's nice about your use of the squeeze theorem. You're never going to have to come up with the functions that bind another function above and below. They're going to be handed to you because they could be hard to find. You're responsible for recognizing the squeeze theorem and finding the limit with the correct justification. So there's three things that are important, okay? So let's just number them. Number one, you need to find the limit of the slices, the bread. Limit of the bread slices. So for us, that's going to be, what is the limit as x goes to -1 of -3x? And what is the limit as x goes to -1 of x squared plus x plus 3? Each of those, in this case, we can find how? Just plug it in. We got a line and a parabola. They're continuous everywhere. So -3 times -1 is +3. And if we plug it into the bottom, we get +1 minus 1, which is 0, plus 3 is 3. Well, that means we keep going. Because what this means is the top function and the bottom function are squeezed through the point -1, 3. So we know it's going to work. The inequality itself is important. So now we're going to state the inequality. And it almost seems like it's unneeded because it was given, but they could have given you all kinds of information. Stating it shows that you know it's important. So you got your limits of the top and bottom calculated. They're the same. So now you could say since -3x is less than or equal to g of x, which is less than or equal to x squared plus x plus 3. And then the third step would be to find the limit that you're asked to find. And if you want, you can actually state the theorem. That's an option. You don't necessarily have to. You're using the theorem, so you don't have to state the theorem. So since the inequality holds true, you could say comma, the limit as x goes to -1 of g of x must equal what? 3. Yeah. Now, I sometimes feel the need to add the word there, too, T-O-O. It just seems right, yeah? Since that one is 3 and that one is 3, that one is 3 also. And if you want, after the word 2, you can even kind of say, by the squeeze theorem. But none of this stuff here is required. Sometimes it just adds a little bit of seasoning to your work. So the things that are important are the limit of the bottom, the limit of the top, the two slices of bread. If those are the same, proceed and say, okay, now since the inequality holds true, the one in the middle has to pass through the same point as well. Not pass through, because remember, it doesn't have to be defined there, but the limit has to be the same. Now, the question always comes up, what if the two bread slices have different y value limits? What if one of them was 3 and one of them was 4? Yeah, that's about all we could do. We could say, since this, then we know the limit of g of x has to be somewhere between 3 and 4. But how many values are there between 3 and 4? Infinitely many. So we've narrowed it down to a small interval, but we can't pinpoint it to anything. And you're probably not going to be given that. When you're asked to use the squeeze theorem, they're more than likely going to be the same y value because they're testing you on whether or not you understand the theorem and how to formulate an argument. And this is it right here. 3 elements. We'll have lots of theorems this year. Okay, that concludes the notes. So here's what we can do. We can go to the worksheet. The worksheet for 1.2 is due Thursday, and I don't mind pushing it off, right? Is that what I said? What did I say? I'm getting confused with classes. That's what I just said? Yeah, okay, yeah. That's fine. We could do that. Let's go ahead and look at the worksheet then. And if you have any questions on it, we could do it now, or we can maybe even look at some together. Not that I want to steal your thunder or anything. But there is typically a question that comes up about number 3. So let's just look at number 3. Are we in here at the 205 or 210? 210? So we have 10 minutes. Okay. Look at number 3. It says the graphs of the function x, which appears to be the one in blue, and negative x, which is the one in red. So those are 2 lines. H of x is the function in green. And we've already kind of seen one like that, where 50 pi over x, as it approaches 0, it's going to oscillate faster and faster and faster and faster. But notice this one has an amplitude that's defined by x. So it's going to be contained in between these 2 lines, which is kind of interesting. As it gets closer and closer to 0, it oscillates faster and faster, but the amplitude is decreasing. We want to use the squeeze theorem to prove, essentially, and find what the limit is as x goes to 0 of the green graph. Now notice direct substitution is not going to work here, because when you plug in, you get a 0 times, this becomes infinity, and cosine of infinity doesn't exist. But you might figure out, if you have the graph, that it's what? 0, and it is. So how do we prove that? Well, it's about the same 3 things. Number 1, we have to state the inequality. Now this one is a little bit different, and in the key on the notes, I use the absolute value, which you could do, but here's another way to do it. Unlike the function that we just saw, or the problem we just saw, it's not the same function bounding it on the top all the way through from -1 to 1. It switches at 0, okay? From -1 to 0, the red one is on top and the blue one is on the bottom. From 0 to 1 now, they switch places. The blue's on top and the red's on the bottom. So they still bind the function in between them, but it's not the same one all the way across from -1 to 1. So we'll have to state it as 2 separate inequalities. Now the blue one on the bottom is what we're calling f. So you could say this. Since f of x is less than or equal to h of x, which is less than or equal to g of x, on the interval from -1 to 0, and you can list that as an interval notation, and then you flip it around. G of x is less than or equal to h of x, which is less than or equal to f of x, on the closed interval from 0 to 1. Now notice there, I did overlap the 0. I put a bracket on both, but that's fine because it's less than or equal to, so it's okay. So this one had to be broken up into 2 separate inequalities because they switched. The top curve was different. So now that we have that, and it doesn't really matter the order of 1 and 2, I actually did the inequality first. Then you could do the bread slices. The limit as x goes to 0 of x by direct substitution is 0. And the limit as x goes to 0 of negative x by direct substitution is also 0. So these 2 steps can be done in either order, as long as they're both in there. Number 3, then, you could say, so by the squeeze theorem, if you want to add that in there now, or you don't even have to say it at all, the limit as x goes to 0 of h of x must equal 0. So again, a pretty easy theorem to understand, but it's the notational argument that you're learning how to formulate. Now this is kind of an exceptional one. I'm not sure if you're going to have one where you're splitting it up, but who knows? You can do it. 4 is a pretty typical one, more like what we just saw on the last example on the notes. So I'll let you do that one. So is number 5. Then you got some multiple choice, blah, blah, blah. Number 9 is a good one. Number 9 is kind of like the multiple choice question I was telling you about. This one has 2 terms, and you're evaluating them separately and then coming up with the answer. Now let me point something out here because this was a little bit confusing. Number 6 looks like it kind of goes with this graph on the worksheet, but it doesn't. It's a standalone problem. And then the graphs, which are below 6, it says here, use the graphs above, for example, 7 through 9. So it doesn't have anything to do with 6. But it does have to do with 9. So see if you can answer question number 9, and you'll be that much closer to getting one right on the test next week. got to be very deliberate, kind of meticulous. It's easy to get your negatives mixed up or approach from the wrong side. Maybe look at the wrong graph, look at F instead of G, or vice versa. Fire drill was canceled today because of impending weather and rainstorms. Not raining out this window. How about that window? No? So, you know, there's two windows out of which it's not raining. Did you get 0? Yeah, good. Good. G of 1 is just a dot, right? Which is at -1. This is -1 evaluated, or x evaluated at -1. You can use direct substitution. And then the function f from the right, -1, -1, and then simplify. So the one on the test, I may have like 4 terms instead of just 2. So you have 2 more things to go, add them together, so on and so forth. Kind of fun. So this worksheet isn't too bad. But y'all do have, I guess, until Thursday because I said that. So do it before Thursday because it's DUE on Thursday. And remember, you're doing it on paper, hard copy. Now, tomorrow we will start 1.3. 1.3 is limits and infinity. And we could probably finish that one in about a day and a half. And we're working towards 1.4, which is the big fun section, 1.4. Probably have a little quiz tomorrow, too, so be ready for that. And I'm here at 7 if you have any questions.